we were talking about dimension. Let us review briefly where we are, and then we will finish with that today.
Oh, I'll do it one, sorry.
Yeah.
These are no one using. We are using them so that they are always.
Okay. Yeah. So we one of the theorems we proved was that the dimension of variety is the same as of an open subset. So X variety U in X open and non-empty, obviously, then it follows that the dimension of X is equal to the dimension of U. And I didn't explicitly state it, but an obvious corollary is if varieties X and Y are birational, then they have the same dimension. No? And so finally the last thing we proved the last time was that if you have a morphism of variety, and we have that there's an open subset in the target where the dimension of the fibers is equal to some number n, then the difference of the dimensions of X and Y is n. So assume this is U subset Y open non-empty such that dimension of f to the minus 1 p is equal to n for all p in U, then it follows the dimension of X is the dimension of Y plus n. So we want to start by giving a few applications of this. So, in this example, the most stupid one is if I have the dimension of the product of two varieties, obviously, is therefore the sum. So we just apply the theorem to the projection to one of the factors. Okay, so that's easy. What else do we have? So another thing which looks a bit more less useful, but we're going to use it in a moment, is that if X in Pn is a projective variety and Cx in En plus 1 to define cone, then it follows that the dimension of Cx is equal to the dimension of X plus 1. And this is again clear because we have a map from Cx to X, just the projection into the equivalence class. So I can write like this: if we have, for instance, x0 to xn, if these are the coordinates on n plus 1 from Cx to Cx without 0 to X is a morphism namely it sends every point in Cx to its class in vector space. And for all p in X, we have that well, f to the minus 1 of p will be isomorphic to C without 0. No, because f to the minus 1 of p is just a set of all classes in the cone whose equivalence class is p, and this is just isomorphic to set of all A0 n.
I think you mean K minus 0?
What?
Not necessarily C. It can be general field, right?
Oh yeah, certainly. I don't know why this group, why the field all of a sudden became C. Such that the class is 0 to n. So is equal to p, and this is just a map which sends. So this is obviously isomorphic to C star because I just have a map to K star which sends. If I choose any representative A0 to n, we have a map from this to this by just taking all the multiples by elements in C star of the one represented. So this is isomorphic, and this obviously has dimension 1. Okay. So now we want to use this to so k without 0, in other words, in 1 without 0. So we want to use this to study the dimensions of intersections of arbitrary subvarieties in A n and T n. And this is the following theorem. So first we find case that x and y in n be defined varieties. We know that the intersection of them must not necessarily does not have to be irreducible, but the statement is every irreducible component of x intersected y has dimension at least the dimension of x plus the dimension of y minus n. Okay, but so one should be aware of the fact that obviously this intersection can be empty, even when this number is positive, because you could have, for instance, two parallel hyperplanes in even a big affine space, and they don't intersect. But we have this statement. You can see this is a generalization of the corresponding result we had for intersection with the hypersurface. So if in particular y is a hypersurface, then it has dimension, at least dimension of x minus 1. So which is the special case of a hypersurface. And the second is the same statement for projective varieties. So let x, y in Pn be projective varieties. So then again, every irreducible component of x intersected y has dimension at least, so it could be larger, but it's at least dimension of x plus dimension of y minus n. This is precisely the same statement as in the defined case, but there's more. Namely, if this number here is not negative, then the intersection will be null. If the dimension of x plus the dimension of y is bigger or equal to n, then it follows that x intersected y is not n. So this is very different from the defined case. So in particular, we see any two hypersurfaces in a projective space of dimension that these two will intersect, but much more general. Just if the dimensions add up at least to n, we get a non-zero, non-empty intersection, and its dimension will be at least this. Okay. So let's. So in particular, we also see if you have any variety, any projective variety which is not a point. I think that we actually had already as an example before. If you have any projective variety which is not a point, and we take its intersection with the hypersurface, then it's not empty. That I think we had before, as a special case. Okay, so now we want to do this. So, well, it's maybe not so clear. So we'll first prove the first one. The second one will be mostly a consequence of the first by using the story with the cones. And so, but even here, it's not at all obvious why this should be true. Until now we only know how to intersect with hypersurfaces. So we know that if you intersect with a hypersurface, the dimension goes down at most by 1. And so, so then, as this is the only thing we can do, we have to reduce to that. So we use a trick. So we use the diagonal to reduce to intersection with actually hyperplanes. So let's look at it. So remember, we can look at the diagonal, which is the set of all P in n in n times n, which is a2n. Anyway, this is the diagonal. And we have the diagonal morphism that delta from En to delta be the diagonal morphism. We used it before, so this would be the map which sends point P to PP. And we know that delta is an isomorphism. And now, how do we use this? So, if we take x times y and take its inverse image, so maybe right there. So we take the inverse image under delta of x times y. So x and y are our subvarieties. What is it? This is the set of all p in n such that P, comma P is in x times y. So that means such that P is in x and P is also in y. So this is just x intersected y. So therefore, So thus, we have that x intersected y is isomorphic. I mean, see, I have to be a bit more careful, but okay. So, well, now, as an algebraic set, at least, it is isomorphic to, so it's isomorphic to x times y intersected delta, the corresponding image under delta of this. No, delta to its image is an isomorphic in A to N. Okay. So we have defined what isomorphism is normally only for varieties, but here we are in a fine space. We can say what an isomorphism is in terms of just polynomial maps, and then we don't need it to be irreducible. And so this is isomorphic. And so instead of this, we can look at this. And so we want to show that every irreducible component of this thing has a corresponding dimension. And now, how do we use this to reduce to intersection with hyperplanes? I claim that delta is an intersection of n hyperplanes. So let x1 to xn be the coordinates on the first vector an, and y1 to yn the coordinates on the second vector. In an times an, then delta is just the zero set of x1 minus y1 until xn minus y. Because to say that 2 points, one in the first vector and one in the second vector, are the same, precisely says that each coordinate is the same. So you can see it's an intersection of n hyperplanes. In A to N. So by this theorem we proved the last time, every irreducible component of the intersection of a subvariety Z in n, or whatever, 2n, whatever, with a hypersurface or a hyperplane, has dimension bigger equal to the dimension of Z minus 1. Because we had seen that if Z is not contained, is contained in the hyperplane, so we had said if it's not contained in the hypersurface, then the dimension is precisely the dimension of Z minus 1. But no, obviously Z could be contained in the hyperplane, in which case the dimension is not, is just the dimension of Z. So in any case, the dimension can at most go down, at most go down by 1. Okay. So dimension is equal to dimension of Z if in the hypersurface F if C is contained in this set of F, and it is dimension of Z minus 1. Otherwise. Okay, so we can make induction. So if we have our X intersected Y, it has so we have X times Y, it has dimension of X plus dimension of Y, and then each time we intersect with one of these equations, the dimension goes down of each irreducible component goes at most down by 1. So in all, every irreducible component of this intersection has at least dimension of X plus dimension of Y minus N. So by induction, kind of intersecting one by one with these hyperplanes. N times with the hyperplane. Every irreducible component of X times Y intersected with 0 set is dimension of X times Y, dimension at least minus N. And now note that as X times Y intersected this is isomorphic to X intersected Y, so thus every irreducible component of X intersected Y has dimension bigger equal to dimension of X plus dimension of Y, because we know that dimension of X times Y is this minus N. Okay, so this is the proof. So we have kind of used this trick with the diagonal. That's somehow the way how you can, if you want to intersect things, it's much easier to take the product and then intersect with the diagonal. Even if you look into whatever the book of Fulton about intersection theory, that's how intersection is constructed. Then obviously there are further difficulties which one has to somehow solve, because otherwise there wouldn't be a whatever, what is it, 600-page book where it's explained how to do intersections in general. Okay, so this was this case. Now we want to deal with the projective case. So as I said, we'll reduce to 1 by using cones. And as before, there will be, as in the case of the, obviously there must be something more than just reducing, because we prove a stronger result in the projective case. So there must be something which helps us to prove more. But that we will worry about later. First we prove the analog. So I look at the cones Cx and Cy in An plus 1. No, remember that we have X and Y in Pn. So it's easy to see. If I take the cone over x times intersected y. By definition, this is just the cone over x intersected the cone over y. Just remember how that's defined. And x will be, x is irreducible, different only if the cone of x is irreducible. So we have, and obviously the same if we put x intersected y over y. So now let z be an irreducible component of x intersected y. Then, I think you should be able now to make the proof. It's quite simple. We know that the dimension of the cone is always one bigger than the thing, and then you just use this. So let me do it. So we have the dimension of, so I should also have said this, that the dimension of the cone over x we had seen is equal to the dimension of x plus 1. So thus, we use 1. The dimension of z will be equal to the dimension of the cone over z minus 1, which now the cone is an irreducible component of the intersection of cx and cy, so we can apply the 1 to this. So this is bigger equal by 1 to the dimension of cx plus the dimension of cy. So we are in now a fine space of dimension n plus 1, so I have to subtract n plus 1. This gives me the dimension of the corresponding cone, of the intersection of these cones. So this would be the dimension of cx, but it's minus 1. And so this is therefore the dimension of cx plus dimension of cy minus n minus 2, which is dimension of x plus dimension of y minus n. Okay, so it's just trivial. No? We just use the fact that the difference between dimensions between the cones is always 1, between the thing and the cone is 1, and then it's just almost a tautology. Now we come to the second statement, that the intersection will be non-empty. So there must be something different from the affine case. And the thing is that these are not, the cones are not arbitrary subvarieties of an plus 1. All the cones have one point in common, which is the origin. So we know beforehand that they intersect. No, because every cone, by definition, contains the point 0, 0, 0, 0. And so we use that. So we note that Cx intersected Cy is not empty because Cx and Cy contain 0. And the point 0, the origin of the space. Now, every irreducible component of Cx intersected Cy has dimension bigger equal to the dimension of x plus dimension of y minus n plus 1. I'm just seeing it in a different way. So it has this, and it's also, so every irreducible component of the intersection has at least this dimension. In addition, we know, so this wouldn't really necessarily say anything, because if we just have this statement, the intersection could still be empty. There might be no irreducible component of the intersection. But we know the intersection is not empty. So there are some irreducible components, and they have at least this dimension. So there are irreducible components of Cx intersected C of this dimension. What is it? Dimension of x plus dimension of y minus n plus 1. So this is actually yeah. So therefore, if the dimension of x plus the dimension of y is bigger or equal to n, then this number is positive. Not just 0, but positive. So if dimension of x plus dimension of y is bigger or equal to n, then there are irreducible components of Cx intersected Cy. So I call them, maybe I call them Cz, because an irreducible component is also a cone, Cz, of Cx intersected Cy of dimension bigger or equal to 1. No, because this is. And so that means Cz cannot just be the origin, because it has positive dimension. If it was just the origin, the dimension would be 0. So thus Cz is different from 0, thus it follows that Z is not the empty set. And so we see that the intersection is indeed not. Okay, so this was the statement. So this was, so to speak, the last result I wanted to prove in this part. But so I wanted to stress that this last statement is rather a rather strong result. I mean, that just if the dimensions allow it, the intersection will always be non-empty. So that's a quite strong existence result. So it's actually something which distinguishes projective space. I mean, it more or less, it's maybe not entirely true, but at least intuitively, if a space has that property, then we would think it's projective space. But at least we can use it. So, so for instance, one thing. I mean, it's kind of, if we have, for instance, Pn times Pm, this is not isomorphic to P, say n plus m, just as an example. And this is just, in this case, how can we do it? So in Pn plus m, any two subvarieties say x and y of dimensions n and m intersect. But if P and Q are two different points in, say, Pm, then obviously Pn times P intersected Pn times Q is the empty set, because we want here the condition would be that the second component, intersection means that all the coordinates should be equal and P is different from Q. So we see that, for instance, the product of projective spaces cannot be isomorphic to a bigger projective space, although we know that they are birational to each other. Okay. So I wanted to very briefly also talk about another interpretation of dimension, which we'll also use later, which is another one which you can also find in many books, which is that the dimension is explained as the transcendence degree of the field of rational functions. So in some sense it should be obvious. We have shown that, so maybe I can write it. I will just sketch it. So, dimension and transcendence degree. We know that, we know that birational varieties have the same dimension. So that I just reminded you of that it's a corollary to the fact that an open subset of the variety has the same dimension as the variety. And we also know that varieties x and y are birational if and only if kx is isomorphic to ky as k algebras. So that means we must be able to express the dimension in terms of the function field. No, because it only depends on kx. So, and so what it will be the so-called transcendence degree of kx over our k. And this also, in some sense, intuitively seems nice, because you could say that the transcendence degree somehow says how many independent coordinates, at least infinitesimally, x has on it. So how many independent, algebraically independent variables exist on it. And so that also is a nice notion of dimension. So now I have to explain to you what this transcendence degree is. So this is some kind of, so I pretend to kind of know it and review it, but it is quite elementary actually. So recall some facts about transcendence degree. So let me first definition. So let k over k the field extension let A1 to AN be some elements of the larger field. Then I had told you what the field extension generated by these elements is. So denote K A1 to AN with round brackets like this. The field extension of K. Generated by A1 to AN. So this is the smallest subfield of K, which contains small k and A1 to AN, and we had this in the last semester. So if I can write K equal to such a field extension given by finding the elements, A1 to AN in K, we say that K over K is a finitely generated field. Okay, so that's simple. So now we study only finitely generated field extensions. So let K over K be such a thing. Now I want to say what the transcendence space is and the transcendence degree is, and what it means to be algebraically dependent and independent. So elements, we'll call them now B1 to Bn, in K will be called algebraically independent. If they don't satisfy any polynomial relation. So that means if there's no polynomial, so f in as many variables as I have here, and obviously not the zero polynomial, such that f of P1 to Pn is equal to 0. So you can see one element B in K will be algebraically independent and in principle over K. But we forget this, but anyway. It will be algebraically independent if and only if it is transcendent, namely if and only if it's not the zero of a non-trivial polynomial in one variable. So if you want to be R algebraically independent, over K, then this K B1 to BR will be isomorphic as a field extension of K to what I had called K x1 to to xr, which is just the field of rational functions in x1 to xr.
But it could be that there is a relation between a subset of the b's. For example, if we have three, b1, b2, b3, it could be that b1 and b2 satisfy a polynomial equation, but the three together don't. And therefore...
No, but... Well, but you see, you don't need to... You can always put one of the variables equal to 0. No, that's still... You know, that the polynomial is not 0 doesn't mean that it has to depend on all the variables.
Yeah.
So in that sense, you're... I mean, that's not the... but anyway, so this you can just... So this is the smallest field extension containing all these elements. And so you can easily see that this... So if you just take all the rational functions, so that means all fractions of polynomials in B1 to BR, one divided by the other, just formally, then this certainly, they form a field, and it is a field containing these elements. So if they are algebraically independent, it follows that the subfield generated by these elements is isomorphic to just the field of rational functions. The field of rational functions in x1 to xr is just formal rational functions. So polynomial in these variables divided by another polynomial with the usual relation. So the fraction field of kx1 to xr. Okay. So and now so if I have a maximal set of algebraically independent elements over K, it's called a transcendent spaces. So maximal set of algebraically independent elements in K over K is called the transcendent spaces. So this means if I have any set of algebraically independent elements to which I cannot add another element without making it algebraically dependent, then this is called a transcendent space. Okay? And so it doesn't, a priori it could be that there would be many different transcendent spaces which have different numbers of elements. But in fact, it's not the case. The number of elements in a transcendent space will always be the same. In fact, the name transcendent spaces is also chosen because everything is very analogous to basis of a vector space. You have basically the same theory. And in some sense, if you know how to translate it, the same proof for the elementary statements, you know that every vector, every field extension, here I only take finite degenerate, but every field extension has a transcendent spaces, and any two bases have the same number. Transcendent spaces have the same number of elements. The proof is, with a suitable translation routine, the same as for vector spaces and bases of those. But you can do this as an exercise. And anyway, so the following theorem I'm not going to prove, but you should be able to do it if you pay attention in the linear algebra course. So let K equal to Ka1 to An over K be a finite degenerate field extension. First, there exists a transcendent spaces and we can choose it as a subset of the generators. So this is the analog of the statement that, if you have a finite dimensional vector space, it has a basis which you can choose as a subset of any set which is generated as a vector space. It's one of the first things one proves. The second one is every transcendent space has the same number of elements. K over K has the same number of elements.
Do we require that this A is not in the base field? Because I can take the same field as an extension of itself.
Yeah, but you see, then this thing is algebraically dependent. So when you choose it, your subset. So you can always add something in K to itself.
Yes, but in this case there is no transcendental elements, nothing. There is no transcendental basis except the empty set.
Yeah, and it has a transcendence degree 0. The basis can also be the empty set. So there is a, so if you take K over K, the transcendence degree is it has a transcendence basis which consists of the empty set. I mean, what's the problem?
Okay.
It's a maximal set of algebraically independent elements of K over K. So, the empty set is, one has to be able to deal with that somehow. It often leads to almost paradoxes, but not quite. So it has the same number of elements, and this is called the transcendence degree. Of K over K. And finally, if we have a transcendent basis, we can look at the subfield generated by it, and then K over this subfield will be a finitely generated algebraic extension, or just an algebraic extension. So let Q1 to BR be the transcendence basis of K over K. And then we take K over the field generated by this transcendence basis, which we know is actually isomorphic to a field of rational functions in variables x1 to xr, is a finite algebraic extension. So it's a finite algebraic extension because we have assumed that K over K is a finitely generated extension. No? Otherwise it would just be an algebraic extension. So now, how does so now we go back to our situation. So now let X be an algebraic variety. Then X will contain an open affine subset. I mean, either it is affine, or we know every variety has a cover by open affine subset. So then X contains an open affine subset And we know that the so x is birational, so v inside some, which is isomorphic to a subvariety in some affine space, so I just view it as lying it. So then kx will be isomorphic to, it's anyway isomorphic to kv because x is birational to v. And this can be written as k, the extension generated by some elements y1 to yn, when the yi are the coordinate functions on v. So just the restrictions of the coordinates to v will be some the functions, the class, so it's certainly these elements will generate, no? Because we know that ax, ab is equal to k x1 to xn divided, so that means yi is a class of x. I know that's what I mean by coordinate functions. So divide by ix, and so yi, so which is the same, if you wish, it's just the what you get if you extend, if you put here, add here the elements y1 to yn, and then if you take the fraction field, you just get the field extension generated by that. So thus kx over k is a finitely generated field extension. So I call just a, so I write maybe transcendence degree of kx for the transcendence degree of kx over k. Which is thing. So in some special cases it's quite easy to see what this is. So for instance, if x is equal to an, or x is equal to pn, then we know that so as a rational, the field of rational functions is the same, and so in this case it's just the field of rational, so the a of x would be in this case just the polynomial ring in x1 to xn, so kx is just the field of rational functions in x1 to xn. So here, this means x1 to xn are algebraically independent and they generate, so it follows thus the transcendence degree of the x is equal to n, which happens to be the dimension of x in this case. And now the claim that we want to show that this is always the case. The dimension of x is equal to the transcendence degree. And we want also to show something else which we want to use. So we will show for all varieties the dimension of x. equal to the transcendence degree of kx. And you see, so just to stress it again, if the transcendence degree is n, it means that kx contains a subfield, which is a field of rational functions in n variables. So it's really, you really see that there are n, algebraically independent functions on it. And so this is also a feeling of dimension. You can either, so you have then two completely different notions of dimension which happen to be the same. One is that if you cut it down by an irreducible hypersurface, each time the dimension, you can, if you do it in the best way, the maximum number of times you can do it is a dimension. So each time, so how fine you can cut it is n, and this one is how many, in a suitable sense, independent coordinates you have, but as rational functions. So, okay. So we want to show that, and so, but for this we will show first something else, and then we want to show. So for this, we will want to show that every variety is isomorphic to a hypersurface, is birational to a hypersurface in a fine space, one dimension height. And from this, the following will only be useful. So for this, we use the theorem of the primitive element. Which you remember, we had this rather painful proof in the last semester. So let k over, well, maybe L of k be a finite field extension, finite separable field extension, then there is a primitive element exists an element, say B and L, such that L is equal to K. The field extension generated by B. So now we have only proven this in the case that the field is at least infinite, and for simplicity we will assume instead that we are in characteristic 0. So otherwise we will have to show that the field extension, so let me just try to say it again. We will use this result to show that every variety is birational to hypersurface in A to the dimension of the right plus 1. In order to prove this from this, one would have to show that a certain field extension that we encounter is separable, which one can, but we are too lazy or we don't want to make the effort. So we will instead assume that we are in characteristic 0 when all field extensions are separable. Okay.
Just have a question. Why it is finitely generated?
Well, that's what I try to prove here. So it's generated by these elements, where these are the coordinate functions. If x is contains an open affine subset, which is isomorphic to a closed subvariety of an, then the coordinate ax is generated by the classes of the coordinates, yes. And therefore the fraction field of it is also generated as a field by these elements.
Yeah, but 1 over y1, for example.
No. As a field, it's generated by them. It's a finitely generated field extension. So the same elements which generate k. I don't need that it's finitely generated as a polynomial ring. It's finitely generated as a field. So that means using all the field operations. So if a ring is generated by some elements, if you take the fraction field, it's generated by the same elements as a field. No? So that's what I mean. It's just a finitely generated field extent. We talk about fields, not about. Okay, so now let me prove this. So theorem, every right x is birational to a hypersurface in some an. But now we know that, okay, for the moment we have that. They didn't want to see that this is. So proof, we assume the factors of K for simplicity. So, as a matter of fact, there are geometric proofs of that. You could say you have X lies in some projective space, you intersect with an open affine subset, and you are in some affine space, and then you can kind of project down from points. And if you're careful, you can do this until you get a hypersurface, by counting dimensions in a suitable way. But we instead do it algebraically, without, so we don't have to think, we just use simple facts about fields. So let x1 to xr, so these are small x's, be a transcendent spaces of kx over k. We know that such a thing exists. Then we have that kx over this thing is a finite algebraic extension. So we can apply to it the theorem of the primitive element. So thus there exists an element y in Tx such that Tx is equal to k x1 to xr. So by adding one algebraic element y. Y must be obviously an algebraic extension, so y is algebraic. So y is algebraic. Over k x1 to xr. So there's a polynomial, a non-zero polynomial, which has y as a 0. So thus there exists f, which is the polynomial in rational function x1 to xr, comma y, then of course x, with f of y is equal to 0. And obviously a non-zero polynomial. So remember that this kx1 to xr is just the field of rational functions in variables x1 to xr. So I can also view the xi just as variables. no? Because they are algebraically independent. So we write this f, you can write it out, so this is sum over sum L. I have some polynomial in x1 to xr divided by some other polynomial times x to the n. So where gl and hl are just polynomials in x1 to xr. Now we can, if we want, clear the denominators. So we multiply the whole thing with say the product of all the denominators, and when we divide by the greatest common divisors of all the coefficients we get. So that f, so the polynomial, I mean in some sense maybe strange to write this one small, but anyway, at f, so this is now polynomial in x1 to xr, x, d, the polynomial obtained by multiplying f with the product of the HL and dividing by the greatest common divisor of the new coefficients. And I have to use something which I then I claim yeah. So I forgot something here. So obviously there exists such an f, and I can choose f to be irreducible. No, because if the product of things is 0 for y, then one of the factors must be 0. So is this ever irreducible? So that means follows that f is primitive. So the coefficients have no common divisor, and its class inside the quotient field, it is irreducible. So coefficients in the quotient field, which is just the field of rational functions in x1 to xr. So by the Gauss lemma, f itself is irreducible. So I should maybe say that this is a bit more, we didn't prove that in the algebra course. In the algebra course we just had looked at the case when we have polynomials over z and over q. Here, instead, we are considering the more general form of the Gauss lemma, where you have a unique factorization domain, which I didn't even define, but this kx1 to xr will be a unique factorization domain. And then if a polynomial is with coefficients in a unique factorization domain is primitive, so the coefficients have greatest common divisor 1, and it's irreducible with coefficients in the quotient field, in the fraction field, then it is irreducible also here. And if and only if. So that version of the Gauss lemma also holds, and that's what we're using. Okay. So thus the zero set of f in En plus 1 is a hypersurface. An irreducible hypersurface. No. You just say f is a polynomial in irreducible polynomial in kx1 to xr, so in r plus 1. And we have that if we take, so I call this y.
Why is a small f irreducible in the quotient field?
I just said that's what Gauss lemma. Oh, because this is, no, I just have multiplied f. So this f is obtained from the small f by multiplying by some products of the coefficients. But these are elements of the quotient field themselves. So if you take a polynomial and multiply the whole thing by some elements in the field, certain irreducibility doesn't change. Okay, now we're almost done. So thus, this defines a hypersurface y equal to zf in this. And so if I take the function field of y, this is equal to the fraction field of k x1 to xr, x modulo d generated by f, and which is same as k x1 to xr because here we have just multiplied by this, which is k1 xr. Y was this element, which is kx. So therefore x and y are bidirectional. So I should maybe have said that what we really have proven is that, so what we really have shown is that x is birational to a hypersurface in A to the transcendence degree of kx plus 1. Oh, that's how what we actually proved. But now, so notice that this shows that in fact the dimension of x is equal to the transcendence degree, because we know that if you have a hypersurface in a fine space, its dimension is the dimension of the fine space minus 1. So that's then the whatever. It's still called theorem, although it's corollary. Let x be a variety. Then the dimension of x is equal to the transcendence degree of kx. And so it's just a fact. We know that x is birational to a hypersurface y in a to the 27th degree of x plus 1. So thus, by our theorems, we have the dimension of x is equal to the dimension of y is equal to the dimension of this affine space, so to this number, 27th of degree of x plus 1 minus 1. Okay. I read just x, but I mean kx, obviously. Okay. So this is how we see this now. So this was as much as I wanted to say about dimension. We'll talk about smoothness and so on next time. Maybe it's not a good idea to start right now. So I anyway went, I mean, so I have still in some sense 10 minutes, although, and so, but I'm pretty sure I will use this another time. So you are not cheated out of your precious lectures. Okay, and we see each other next week. I don't know when. Okay, so